when I talk to a lot of different companies I consult with, I think, when people find that the retrieval systems are not catching the nuance of their data set, it usually comes down to, asking ourselves, like, are we able to fine-tune embedding models or fine-tune re-rankers? And what is the expected sort of like effort and what is the expected return on that investment? In a lot of cases, we do see, 10 to 20% improvements in recall. And so today I'm really excited to invite Ayush, an ML engineer at LanceDB, to show us some of the results he's been working on. And, I saw a lot of different experiments and tables on cross-encoders and ColBERT, and I'm really excited for him to share in the next couple of minutes how he thinks about mapping out the space of re-rankers, when to fine-tune, and when to combine all these results to get the performance you need. And as always, if you check in the Zoom chat, we have a Slido link there. You can ask your questions and we'll be able to upvote questions that are popular. And then we'll do questions at the very end. And yeah, with that, Ayush, take it away.
Awesome. Thank you. We'll cover re-ranking, fine-tuning re-rankers, and then there's a small section about fine-tuning embedding models as well. A little bit about me. I'm an engineer at LanceDB. I previously was at Ultralytics, where I co-authored Ultralytics YOLO framework. And before that, I was doing ML at weights and biases. So the topics that we'll cover today are re-rankers, what are they, why you should use them, and then training or using off-the-shelf re-rankers and fine-tuning them, and when you should do that, what are trade-offs involved, and then we'll talk about embedding models as well. So jumping right into re-rankers, I just wanted to give you a quick overview of where re-ranking fits in. So I'm not going to talk about RAG too much, but I'll just say that based on the definition of RAG, which is there's multiple ways to look at it. The way that I like to look at it, RAG is that RAG is essentially a system where you're guardrailing LLMs by providing necessary and sufficient context that can answer a query in order to prevent them from hallucinating, right? And with this definition, it is very clear that the quality of RAG pipeline will be only as good as the quality of retrieval, because that's what provides it the context, right? So then the job comes down. If you want to improve a RAG, you need to just improve your retrieval. And again, there's a wide variety of things that you can do to improve a retriever, which involves re-ranking, tuning re-rankers, embedding models, using different embedding models, tuning them or training them from scratch, or using advanced retrieval techniques, combining search techniques like full text search, hybrid search, things like that. But I think in every project, you should probably start with the low-hanging fruits to get a sense of where you're going, right? And re-ranker is something like that, which is why I really like it. Re-ranker it's a low-hanging fruit because it does not disrupt your pipeline. You don't need to re-ingest the entire data again into your embedding pipeline or RAG pipeline, because especially if you are someone who deals with billions of or millions of entries, because you can just simply plug and play with re-ranking. So it fits in after retrieval and before the context is provided to LLM. What is a re-ranker, right? So in general, when you retrieve something from a vector database or any kind of database to provide the context to LLM, you get certain documents. Now, the embedding model gets these documents, and we're assuming throughout this talk that we're using semantic search for retrieving documents. Obviously, there are other RAGs or RAG systems out there that don't use semantic search, but our talk is limited to this. So once you got this document, you can do better by rearranging them such that the document with most relevance with the query ranks at the top, right? And this is what re-ranker does. I want to talk about a few architectures briefly, and then we can move into the training part and then benchmarks, because this is really important as to why re-ranking is so powerful. Bioencoders are, you can think of all embedding models as bioencoders. They simply take two or more documents and they get the embeddings or calculate the embeddings independently. And so there's no interaction between documents. Cross-encoder, on the other hand, it takes document and query pair, and then it calculates cross-attention and basically processes both of them together, and they can attend to each other throughout the pipeline. So they're able to get the similarity much better than independent embeddings. So this is why these models, cross-encoders, have been generally used as re-rankers. There are other architectures we'll come to, but this is the general context. Now, the question arises, why not just use this for retrieval directly, because it's so powerful, right? The answer is it's also very compute intensive. It's not a real-time operation across thousands or millions of documents, because you're comparing the query with each and every single document. So this cannot be done at scale, but once you narrow down to top 5, top 10 results in your top K setting, you can then do that. It will just take a few milliseconds. Right? This is why re-ranking is powerful. Okay, how do you train a re-ranker then, if you have to? This is a very simple pipeline for training a re-ranker. And this is also, I mean, when we're talking about sentence transformers, this is why I really like sentence transformers right now, because they come with right defaults. You can do all of these things in there. So the way to train a re-ranker is you start with the data set, and the data set is query context pairs, which is similar to an embedding model. Or you can use it in different ways, but here we're using it for re-ranking. So in this benchmark, the data set that I'm using is Google's QA data set. And it has 3 million query context pairs. I get 2 million out of them, and I will use 5,000 for evaluation purpose, right? And the format is pretty simple. Because you want to train a ranker model, you provide an anchor, which is the query, and a bunch of positive and negative examples, or simply one positive or many negative examples, so that you can train a powerful ranker model. The best trick the recommended trick to use here is to mine really hard negatives, right? So that your model understands the nuances. So the hard negatives are those wrong answers that are very close to the query in an embedding space that is similar to query, right? So these are hard negatives. So to mine hard negatives, generally you use an independent embedding model, right? Which is not in the part of the RAG pipeline. So this is like the general way to use it, and then you use whatever loss functions you like, and all of the re-ranker losses as well. But this is the general setup, right? And yeah, that's pretty much it. The second architecture that I want to talk about is ColBERT architecture. Training them, both of them is the same. The training processes are the same, but this is something new that became really popular in the last 2 years, and rightly so. So you might, from the previous 2 slides, you remember that cross-encoder is really powerful, but super slow, because it has to attend to both query and docs during the retrieval time, right? ColBERT architecture is a late interaction model, which does this same thing in stages. So it independently calculates the document embeddings, and offline, and you can store that as in a vector database or something. And in the query time, it just compares the token level embeddings with the query. So it still attends to the token level features, but it does that in 2 stages, right? So the part that can be calculated offline is already saved in a vector database or whatever architecture you prefer. And then in the query time, you just have to perform this maxim operation on token level to find the best similarity score. I'm obviously super simplifying this. There's a lot more going on here, but this is the basic bird's eye view of what's happening in a ColBERT architecture. But again, other than this, in loss function, everything else remains the same for training both of these models. So, once you run this training step, let's see some of the benchmark results. So simply, I'm using LanceDB here. Obviously, I'm from LanceDB, so I'm using LanceDB. But regardless of what vector database you use, the basic takeaways of this slides and this talk is not going to change. With LanceDB, we've had, because I've used a lot of re-rankers, so I've already built integrations with a bunch of re-rankers. So you can simply just import them and pass in the model. That's it. Okay, so experiment setup. As I already said, we're using question answer data set, and we will use 2 million rows for training. And for testing, because this does not become yet another toy example, I wanted to make it a little bit challenging. So I'm using 100,000 rows that are not seen by the training data set. And from that, we'll try to retrieve 2,000 samples and check the hit rate. Right? So obviously 100,000 is not too big, but it's also not a toy example. The models used for training re-rankers, the base models, right? So we're not going to use dedicated re-rankers just yet. We will train some from scratch and then also compare them with off-the-shelf re-rankers. So yeah, mini LM, which again is very small, easy to train, easy to test out, and then easy to judge if re-ranking does something. And then modern BERT. Modern BERT is a modern version of BERT, with a bunch of improvements on it, trained by Answer.ai folks with, I think, collaboration with Light-On folks. And it only has 150 million parameters, but it sort of performs much better than even billion parameter models or something like that. Okay, so these are the ones that we'll use for training re-rankers from scratch. So we'll attach like re-ranking or cross-encoder or ColBERT heads on top of these base models, base encoders, and then train them to perform as re-rankers. Right now, they are not re-ranker models for like as a base model. So a bunch of control experiments. I mean, you don't have to remember all of this. I'll give like a brief, I guess, summary of these later on. But just to run this experiment, I used two baselines for at top 10 and top 5 hit rate. So at top 10 on this data set, we get 60, and top 5, we get 48. And then base model performance in re-ranking, as you can see, it just outputs gibberish because, again, remember, these are just random weights at this point because we've attached new re-ranking heads. So this just proves that, okay, by default, they are not good re-rankers at this point. Again, you don't have to remember this, but just to, these are the summary of results that we get from training these models from scratch. The naming convention is the re-ranker base architecture used, and then re-ranker architecture used, the re-ranker heads, which is cross-encoder or ColBERT or whatever, the base architecture used, and the negatives, like number of negatives we mined. So you might have seen some slides ago that you have to mine hard negatives, how many negatives we mined at the time. So, I mean, the results to note here is that vector search sort of improves at top 5. We got 48 and it goes up to 60, which is like 12% increase, or 61 actually. And then full text search also improves a lot. From, I think, 36 was the lowest, or 37, and then it goes up to 51. Hybrid search, I mean, this is altogether another talk, because there's a lot to say about hybrid search and advanced retrieval techniques. At LanceDB, by hybrid search, it means combining full text search and vector search results and then re-ranking them to get top K. That's our definition. Obviously, hybrid search in general means combining multiple search sources into one, right? So yeah. The same thing happens with at top 10. We see a lot of improvement from 60 to we get 66, 67, and same thing across full text search and hybrid search. And across architectures, ColBERT architectures, cross-encoder architectures, and others. So jumping to key findings here is that vector search results improved at 12% top 5, and then 6% top K. And FTS also saw some improvements, with some models going up to 20% because we go from 38 to 57 or something like that. Then architecture comparison, right? What do you actually take away from this is that modern BERT in this particular experiment saw the strongest performance. And this is also expected, right? Because modern BERT has 150 million parameters, and the other model that we used was just a toy model, 6 million parameters. So it wasn't much of a competition. But again, the takeaway here is that even a small model, going back, can improve the base performance, because all of them have also improved upon the base performance. So even slight re-ranking with a toy model gives you some improvement. So I mean, I like to see this as a signal, right? So for example, if you're not sure what to do with your data, whether you should use a re-ranker, whether you should tune a re-ranker or whatever, right? Maybe try a small toy model well, you can just train or tune it in 30 minutes, an hour, and you get some signal as to, hey, this works. Let's do this process with a much better dedicated model, right? So that's what I sort of think about. And yeah, so this is just re-ranking performance, and in summary, it ends up improving the results a lot. But can we improve it further? Up until now, we've trained them from scratch. These are not re-ranker architectures that we use off the shelf. So the next thing is, can we also like just use existing re-rankers and fine tune them, right? And if so, what the results are. So these are the baseline performance of dedicated re-ranker models, and the re-ranker model that we are going to use here are Answer AI, ColBERT version. So Answer AI created another model for re-ranking as well, similar to Modern Bird. They do a bunch of other retrieval research, and it's called ColBERT Small. And by default, that gets us 59 from the baseline of 48. So it already improves the off-the-shelf model, improved it then 10%, and then 68% on top 10, right? So I fine-tuned those models as well with the same script, the same settings, and I ended up improving this as well by a couple of percentage. I think 3% here and 2% here. So again, fine-tuning is much simpler, and it still ends up improving the performance. So the takeaway here is that, when I talk about, if you should train a re-ranker from scratch or fine-tune it, it comes down to these two things to consider, right? If there are no re-rankers available for the base model of your choice, you have to train it. There's no other choice, right? Let's say you want to use some fancy architecture of base model, like base encoder, as a re-ranker. You really like it for some reason. You think that's great for your pipeline, and if there is no base model available, just train. The other way to think about it is like, if your data set over time has become specialized enough, we might call it drifted from the original data set the model was trained on, you have to tune the model to then align the distribution. And things to be careful about when training the models, right? These are things that have to be careful about, absolutely, because sometimes you end up using a lot of compute resources as well as time for training these models. And the general rule to remember is fine-tuning converges much faster. Obviously, all of the weights are not random. They already have some context. So training them, the losses will converge much faster. And catastrophic forgetting, right? Like if you fine-tune for a long time on a low-quality data set, whatever the model performance is, it starts to degrade from its baseline. So you have to be careful about that as well. These are two things to consider when you're thinking of re-ranking. Now, obviously, the results that we just saw, you can end up improving, performance by, hit rate performance by 10 to 20%, depending on the algorithm you're using. There are some trade-offs involved. There's no free lunch theorem states. So what are the trade-offs? Obviously, because we are adding a step after retrieval and before the retrieved documents are sent to LLMs, there will be some latency. So I have a latency comparison graph here, and the latency here is calculated on L4 GPU, which is pretty much like a T4 GPU with a larger memory. Why I'm using this GPU is because it's the cheapest and most easily accessible across all collabs, right? Obviously, if you're using a powerful setup, you're going to use much more modern GPU, much faster GPUs. But this setup is more reproducible for everyone. So no re-ranker. Oh, another thing that I want to call out here is that someone might notice that no re-ranker, which is like the fastest, is pretty much slower than cross-encoder train on mini-LM. It's just a numerical instability. Mini-LM is so small that it's not really relevant. It does not really add any significant latency to the GPU when running on GPU. So it should be equal to the baseline case, but it just so happens that sometimes you do model loading and all of that, you get this number. I've left it here because this is a practical case. Sometimes this happens. And so if you average it across thousands of runs, this will just be the same. Okay, so you get baseline here, and then ColBERT, which is modern BERT architecture, it sort of adds 30 millisecond latency. ColBERT on MilliLM is pretty much the same because again, this model is so small and we're running on GPU, it does not add any latency, but you get the idea, right? It adds a few tens of milliseconds to the latency. And the bottom chart, it shows this sort of an ablation study for larger limits, because re-ranking is only powerful if you fetch, large amount of, like, overfetch some documents. If you only need 5, maybe fetch 20 and then re-rank them, right? So this sort of gives you an idea that the slowdown factor is, even if it's by 2 or by 3, these are the numbers in milliseconds. So slowdown factor, depending on your use case, I think for general use case, it's not too much. But if you're in that edge use case where the latency is very critical, then it is significant depending on the use case that you are working with. This is the main trade-off. I was curious about how the performance trade-off is on CPU. So I did this on CPU as well. CPU, obviously, the latency is much larger, or the penalty is much larger. So again, here, the baseline we see is 53, depending on the system that we test. And it adds up to like 3 to 4x, depending on the architecture that you use. So, by the way, the best performing model, which is a dedicated re-ranker by Answer.ai, it does not really add a lot of latency, as you can see. The one that we experimented with was using really large encoder, 150 million parameters. It adds most latency, up to 5 times. But ColBERT's, which is the best performing re-ranker that we have, you can see 68. It does not really add too much, considering it's a CPU. Anyway, so rather than asking the question, who should use re-rankers? Re-rankers are sort of such a low-hanging fruit. I think everyone should by default think of at least trying them out. So I don't ask this. I probably should say you should ask who should not use re-rankers, right? So first, that I already discussed, if latency is keeping it low is really critical, like even 10 millisecond latency added to your pipeline is critical for you, you should probably not think about using re-ranker. You should skip to other ways of improving your retrieval system. And then in all other cases where a few 100 millisecond does not mean much, I think that's the general case, right? Like even network latency, like network round trip from any service takes more than that. So I think it's fine for most cases. So you should definitely think of exploiting re-rankers. Okay, so this is I think is re-rankers. I think we have, okay, yeah, I'll be very quick from now, ahead from this section. Let's talk about fine-tuning embedding models. So as we've already seen, re-ranker fits in after results are fetched. Where does embedding model fit in? Is like in your retriever, when you retrieve data, when you ingest data, you're ingesting data, metadata, and some embedding representing that data, right? And you create all sorts of vector indices on top of that. So, I mean, to give you a bit of context, what embedding model does is it learns representation of a specific type of data. If it's a text only embedding model, it basically learns how to represent text in a given embedding space, and with the goal that data points similar to each other lie very close to each other in that embedding space, right? That's the basic idea of what an embedding model is. And to train that, we use the same pipeline again. Just the loss function will differ. We are going to use multiple negative loss and then triplet evaluator here. That's what I did, and the links to all of the code and all of the experiments with weights and biases charts is all open source. This will be provided in the detailed blog later to you. But yeah, the idea is pretty much the same setup, same data set. Okay, fine-tuning result. And by the way, like I've used MiniLM here for everything. So it's like very small, very easy to train. Baseline, again, 48, as you've already seen, it does not change. And then with different, it's an ablation on epochs, basically. So we get up to 58. So we are improving by 10% by just fine-tuning it. So it is also pretty useful, just like re-ranking. Same thing with top 10. it improves by almost 10%. But now the question is, should you always fine tune an embedding model that you're using? If not, then how to decide or how to make an educated guess? Because in this domain, I should sort of give you a disclaimer that when you're talking about should you train or tune, there is no right answer. There are only educated guesses based on data, right? And based on my experiments that I've done, some mentioned here, some not, this is what I think you should do. I find this as the ideal scenario for fine tuning, right? So the training data that you see in green is the data on which a base model is trained. So let's say you pick up a BERT model and then you try to fine tune it. So this green part represents the data on which this was trained by whatever organization you're fetching the model from. And the fine tuning part, which is the red part, is what you're going to fine tune on. Now, if your data set that you're going to fine tune on is pretty much a subset of the original training data, you're not going to improve the results. You might pretty much end up overfitting the model on a specific subset, and which leads to catastrophic forgetting and which leads to bad performance worse than baseline. The ideal scenario is something on the right. Right? You have a domain-specific data that sort of has drifted apart in terms of its distribution from the original training data. So your model, your data set now, or your use case now has enough new context to be learned by the embedding model. And then you should fine tune it and you'll see much better results, right? Provided, and as you can see in this diagram, I also have a larger size for the red. So which means that your data set that you're going to fine tune on has to be sufficiently large. You cannot fine tune for 10 epochs on 10 examples and train a good model. That's not going to happen. Again, all of this is, it's a hand wavy sort of a napkin math situation where I say, okay, your data set has to have a neo distribution and it should have at least a few tens of thousands of query context pairs, right? But you get the idea. So the left diagram pretty much represents the squad data set. So there's a data set called Stanford Question Answering. It has 90,000 rows, but it's so common that it's not specialized. Like it's not specialized in terms of the questions it asks. So it's, for example, by specialized, I mean legal data or medical data, things like that. By general case, I mean anything that GPT models are trained on or Claude or ChatGPT is trained on, right? So the left sort of represents that. Most standard embedding model data sets already have squad as their subset. And so if you're going to fine tune on squad, it's going to be overfitting very soon, or if you still continue to do it, it will sort of start to degrade in terms of performance. The previous data set that we used was sort of the question answer data set with 3 million rows was again a general data set. It was not a medical data set, not a legal data set, but it was so large that it sort of sits somewhere in between the two, right? So we saw some performance. And towards the end, it started to overfit. But by that, I mean like the best performing model was not the model at 10 epochs. It was somewhere around seven or 8 epochs. So that's the basic idea, right? This is why I spent a lot of time on like this slide. But yeah, just to get that idea across. So to prove this hypothesis, let's train on squad dataset and see if this sort of holds, right? So you see, when we train for 10 epochs, it starts to overfit very soon. And you can see only 3 of the fine-tuned models on this dataset perform better than the baseline at top 5, right? So this is the result that you'll get. Another important thing that generally to tackle the problem of less data or bad data people try to employ is called data augmentation and synthetic data generation, right? Again, this is a very important topic because the concept of augmentation and synthetic data generation is sort of, I have personally seen that a lot of times these are being used interchangeably, which is not right. Because what really happens is data augmentation is not a solution to bad data set, right? It's a solution to generalize an already a good data set with more examples so that it does not overfit very soon, right? So that's the reason why you augment data. And then synthetic data generation is creating more examples out of a good, already a good data set. The problem with synthetic data generation is why I don't recommend you should do that off the bat, is that first, you might not even know if your data set is great to begin with. Right? Run some experimentation. Second is that synthetic data generation happens through LLMs, and it has been found. I don't have the exact like research paper or the docs, but it has been found that creating synthetic query context pairs out of existing dataset, LLMs can hallucinate. Even the good ones like GPT-4 or something can hallucinate up to 70% of the time. So you are creating rubbish data and adding them to your dataset. So you don't know that. In fact, there are some open source tools, maybe well funded as well, I'm not sure, that pretty much measure the quality of the synthetic data generated. And I think I read some blog there that they get up to 70% of hallucinations in this setting. And I've not included any results here, but I tried this with Squad, and after synthetic data generation, even at one epoch, like I could not get anything better than baseline. It was always bad, worse than baseline, right? So be very careful with this as well. Anyway, so fine tuning, and we've seen re-ranking and fine tuning both. Should we or could we combine them? Obviously, yes. So here's what I'm doing. So baseline was we started with 48 and 60, top 5 and top 10 respectively. The best embedding tune model is it goes up to 62 and 69, and then we combine them with the best re-ranking model. It goes up to 64 and 71 respectively. So there's a bit more performance to be squeezed, so you can combine both of them, and then here at this point you can decide, okay, there are trade-offs involved with re-ranker. The trade-off is what? Some latency is added, right? So if I don't want that, let me eliminate that. With using different embedding models, the trade-off involved is very disruptive to your pipeline. If you're someone who already has hundreds of millions or billions of entry points in your database already, you have to re-ingest everything. So it's not cheap, it's not fast, but if that's the direction you want to go because the latency is really, really critical, you can do that as well. Now, there are things to be said about this, that, okay, you can prevent that from happening by using some matrioshka embeddings or tricks like that. But again, that's beyond what we are discussing here today. So yeah, I think that is pretty much the content that I had for this. So yeah, that's it. Any questions? I'd love to answer.
Awesome. Let's jump into a couple of questions, and then maybe we can have another conversation about some of the training stuff as well.
Yeah.
First question from Damien is there any value in using a re-ranker if your workflow already uses an LLM to review the outputs anyways? I don't know if I understand the question completely, but let me know if you have any thoughts.
Yeah, I think I understand that. So so the LLM or all the LLMs can be used as a re-ranker as well, because a job of a re-ranker is to get the query and a few documents and then rank the documents based on their relevance with the query. So an LLM can also do that job. You can just prompt an LLM saying, okay, here are the docs, here's the query, how would you rank them, and then get the rank. In fact, I implemented something in LanceDB, which is in beta, because LLMs don't always output the right thing. So yes, you can do that, but it's the slowest possible way to re-rank a document. Right? It takes anywhere from few seconds to, if you're using very powerful LLM, depending on API instability and things like that, it can take up to 3 or 4 seconds. So yeah, yes, you can do that. It's just probably not recommended if you're using an API. By the way, this talk totally dealt with open source re-rankers. If you're willing to use an API, if you want to use it, I would personally recommend go for a dedicated API for re-ranker like Cohere does. Cohere has a great re-ranking model. I mean, when I add Cohere to all of these benchmarks, you will see that it blows away all of them, but it was not open source. You cannot fine tune them. You cannot do a bunch of other things on top of them. So I did not add it, but there's a section in the detailed study that will be provided to you about that. But yes, you can use re-ranker, LLMs as a re-ranker, but I don't think you should for various reasons. Yeah.
Makes sense. Another question, which is pretty good, is can you please explain how to prep and detect hard negatives?
So hard negatives right now, the way this is being done in this pipeline, as in the code, is that you take the corpus and you use an independent embedding model, not the model that you're using for your RAG pipeline. You can also use that, but it's recommended to not pollute your pipeline. You already know the labels. You already know the right answer to the context. So you then find the wrong answers, the negatives that are closest to your query by the embedding model. So it seems like it's the right answer, but it's not, and you want to train the model on that. So that's the simplest strategy, because it challenges the model to learn the right thing and not just learn the similarity. So yeah, that's how it's done right now. But there are other strategies as well, other algorithms as well, in implemented in sentence transformers. But I have not dug deeper than that because I did not need to at this point. Yeah.
That makes sense. I guess I'd also call out one fact is like if you actually, build a product, for example, there's other ways of finding negatives, right? One of the companies I worked with, we had a pretty robust like citation UI. And one of the tools we could do is, if we cite something and then the user deletes the citation and asks us to regenerate an answer, that is a very strong negative signal. It's like not only was it in the context, the LLM cited it and it was irrelevant.
Yeah.
And a lot of what we've been doing now is actually basically going like, first we'll do our recall evaluation at top 10, top 20, and then use an LLM to just propose a couple of negatives to verify whether or not we're good at detecting negatives. Those have all been pretty good tools. Yeah, another question around the negatives is, can you give a real world example of some of those fine tuning and the context around it? Maybe you can go first and I can follow with that if you want.
Sorry, I did not quite understand the question. Can you
I think they're just real world examples of fine tuning and re-ranking models.
Okay.
Give the context, models such as legal, healthcare, all.
Yeah, exactly. So I think any point in time where you have sufficient data and that's like it's not generalized. So when you think of when you're thinking of like, I don't know, I'm not going to name companies, but there's a lot of large companies that are making a lot of noise in legal sector, right? So what really ends up happening is that when you start to ask specific questions, even today, if you try it with any of the best LLMs out there that are trained to answer questions, I think they start to hallucinate when you start getting into rabbit holes. That's only because the general training data set on the internet does not contain all of that information, or a lot of that information is proprietary. You might not have the proprietary information of some drug manufacturer or things like that. So at that point, you have to fine tune an embedding model, or even LLM if you're building RAG on top of it, and that's what generally people also end up doing. But yeah, that would be my 2 cents. Like if you're in a specific domain, fine tune embedding models. But yeah, sure. Go ahead, Jason.
Yeah, I mean, I think another part of that too is like if you understand what kind of queries people are asking specifically, then you start thinking about doing something like data generation because you know what the specific use case is, right? Like, it's one thing to just have like arbitrary pairs, but if you know that the questions are going to be around, timings, it's like, okay, well, do we understand that words of the query do not necessarily embed to the text in the text chunk, and we need to sort of close that gap? That's when fine tuning is also very valuable. Other examples I've seen are where, project names are just like, like within like 3 years of Jira tickets, like, okay, well, they have other meaning that isn't encapsulated in embeddings, and turns out, you have a team in Japan and all the projects are Pokemon names. How do you make sure that's like learned in the model? Those are some silly examples, but I've definitely seen that happen in practice. I also want to call out, like, I think people are having a discussion on like, what's the best model, right? And it's never going to be the case that the model that is the best is the one that has the best performance, right? It's always about this budget that you're trying to figure out. What is the maintenance cost? What is the, inference complexity? What is the latency? And then what is the performance? And then you have to kind of consider them as a portfolio of budget that you have to manage rather than just going, well, yeah, I would love to use O3 as a ranker, but it takes too much for API, and it is much better. But it really depends on your use case.
Yep.
I think this might be mostly addressing the fine tuning, but have you experimented with these like linear adapters for these embedding models?
No, I have not.
This like one yet. Yeah.
I think but what I think is like there has to be a lot of, I've not yet started to work on this, but there has to be some follow up to this, because this is just 2 ways of many things that you could do with a retriever, right? I think there's a bunch of other things like, what vector indices you use. This is probably just HNSW or default, whatever LanceDB uses. Or like when you're thinking of hybrid search, does that hybrid search mean one vector column, one full text search column, or two different features, and then things like that. So I think the next direction that I'm thinking of, and I think I've seen some good results, is multi-feature, multi-index search, which is quite interesting at this point for me. And I might do something on that. But yeah, right now I've not experimented with linear adapters.
Yeah, I would love to introduce you to Daniel from Superlinked. He does a lot of like encoder stacking, and so you can do queries like, affordable hotels that are under this price, and
Right. Okay.
cost
Yeah.
that, and like half of that is embeddings and half of that is filters. See some really interesting results there. This was an interesting one. What method do you refer to by fine tuning? There's other methods in fine tuning LLMs that are less prone to catastrophic forgetting.
I think this is not a problem of LLMs. It's a problem of training models in general. Like you see this in computer vision as well. It's just that, the model, I guess catastrophic forgetting is a term given like in the LLM era, but it's just that beyond overfitting, if you continue to train, model does worse. It's a general phenomenon, I think. So I don't think you can really solve this. It's just I think it's just natural that models will start to forget or perform worse on the baseline if you keep on training with bad data set. So there's a bunch of ways to avoid that, and like using right defaults, decent learning rate schedulers, and not using crazy epochs. Like for fine tuning, 5 to 10 epochs is fine. If you're training for 100, you're probably just pre-training, things like that. The general rules of thumbs are good to follow. I think I've only ever seen catastrophic forgetting in action is when I knew the data set was bad and I continued to train anyway, right? Other than that, I have not seen it happen accidentally. So yeah.
Yeah. Almost like a personal request. I would love to see ablations on data volume. I think, I would love, like, what does the performance look like for 5 epochs at 10,000, 20,000, 50,000? I think a lot of people don't really have good intuitions. At least I don't have any good intuitions now on how much data do I need versus the quality of data, right? I think there's been examples where I think people from Gen say, oh, if you have incredibly high quality examples, you might only need 100 stuff into a really, really like smart LLM. But embedding models
Yes.
are also very different. Like, do you find that larger parameter models need less data? Do they need more data? I feel like 10 years ago I had an opinion on that, but now.
Yeah. I think, yeah, I don't have opinion on that, but the thing that I do have opinion on is if you have a really high quality data set with only a few examples, generating like augmenting it by synthetic data set generation, it will end up generating much better data set. So I would say if you have 1,000 pair of really high quality data set versus 10,000 pair of just a bad data set that has conflicting query context pairs, things like that. I think with that 1,000, we could, like, after some operations, turn it into a better data set than that 10,000 data set. So yeah, I think that I have an opinion on. I think right now, again, I also don't have an opinion on the size in terms of embedding models. In CV, yeah, there is an opinion to be had that you need a lot more data, but I think right now I've not seen that. Yeah.
Oh, one question popped on the bottom, which I think is really important to address, which is when using rankers, how do you decide the filtering threshold?
Filtering threshold meaning like the fetch factor.
Yeah, no, yeah, I think in this case he's talking about the filtering based on the score, which I tend not to do in practice, right?
I'm still not sure if I get the question.
So when you re-rank, a document in a query, the re-ranker produces a score. Maybe it's a 0.2, or maybe it's like I think how you decide on what that filter should be.
Oh, okay.
Or whether you should do that in general.
Yeah, I mean, the score that you're getting is pretty much a similarity score that the model thinks, the re-ranker model thinks. So it pretty much becomes like the distance score that you get when you're retrieving using an embedding model, right? So at that point, that becomes irrelevant because you've already retrieved. So I then treat the re-ranker score as the actual score, and I don't really filter on top of that beyond that point. So when the re-ranker says that's the best document, I then stop thinking about it and I say, okay, that's the best document, right? At that point.
Yeah. Generally, I also call it the fact that different models tend to have different distributions in what that score looks like. And so I've worked with companies where they set like 0.5 because they believe that 0.5 is this measure of relevance. And then when they switch embedding models, turns out the average cosine similarity of eta 3 is 0.7, and all of a sudden they have documents in the context. And so
Okay, yeah, and that
keep
makes
to think about
sense.
the ranking
Yeah.
the more number itself.
Yeah, in that sense, what I like generally when I like in these experiments, because I used the LanceDB integration. So what that integration, what that does is it basically normalizes those scores, right? So the model can pretty much output like between 0 to 1, or it can do like non-normalized scores, but there's a normalization step. So it pretty much becomes like a in the same domain as the distance, like same range as the distance from. And so it's really easy to interchangeably use the distance of the vector search algorithm or the re-ranker interchangeably. Yeah.
Yeah, that makes sense. There's a follow-up question, which is how do you reliably generate citations? There's going to be a lot of different techniques. I'll probably just mention this in a blog post rather than just sort of describing all the different ways you can hack XML. But a lot of it is, if you include the chunk ID as XML as you represent the chunks, then you can ask the LLM to reference the chunks, right?
Yeah.
If you want to do more than that, you can not only reference the chunks, but maybe the first couple of words and the last couple of words within the span and generate citations there. But a lot of it will be around experimenting with the XML representation of the spans. If you look at Anthropic or if you look at Cohere's LLM APIs, what they're really doing behind the scenes is this sort of XML citation, chunk ID 7 behavior, or URL, 1, 2, 3 behavior. This is a question I'm curious about for you, which is what is the best way for non-researchers to keep up with the latest developments in AI right now? Do you have any like places you read?
Yeah. I because I don't happen to I happen to work in this, so I think I keep up to date by default because someone sends me some links here and there. But I do have an opinion on how non-technical folks can keep up because I have a lot of non-technical friends who work in design and other things. So I think what I recommend is that you should start to use AI as soon as possible in your workflow. And once you do that, you pretty much become I should not say technical, but you pretty much become a semi-technical person because even being okay, this is an opinion. Like ML engineering 10 years ago was different, right? A lot of ML things don't apply to LLMs. If you are really good at training ML models, stat models, and then NLP models, it does not make you automatically great at training LLMs or embedding models, things like that. So you first to become a user. So I think when someone drops something and then Anthropic drops a new model, run deep research, use all of that. So if you know that, for example, for deep research, let's say you prefer OpenAI or Gemini and Anthropic, you pretty much know that you have to use OpenAI's deep research API if you're building an application on top of it rather than Gemini. So I think being a user is the first step. Beyond that, you'll just keep up automatically. At least 80% of the things that technical folks know, or you might know that. It's just an opinion. I'm not sure how correct or wrong that is. So yeah.
Makes sense. That makes sense. We mentioned that Simon Wilson's blog is very good. It is very good. We'll make sure to add that back in the follow-up notes beforehand.
Yeah.
I'll ask one more question, then maybe I'll ask you a question as well. But the question is, can someone explain the business benefit of all of this, or is it just an academic exercise? I would love to comment on this if you don't mind.
Sure.
Which is the line I tell companies that are very large is if you're not fine-tuning your embedding models or your re-rankers, you're probably closer to like Blockbuster than Netflix, right? At some point, these changes in the performance of these models are going to correlate with some kind of, business outcome, right? Be the re-ranker is actually for product recommendations. And the higher the re-ranker scores, the less returns you're processing or the more volume of content you're selling, right? Same with Netflix. Like they have embedding models for users and content and, making sure that if this little carousel on Netflix shows me 5 videos, I better click on something in the top 5, right? In here, like top 10 means I have to scroll and now there's some issues. So as long as you're building products for humans, then these re-rankers, matter a lot and make a lot of sense. If you're building for AI, it's going to be different because you can provide AI, you know, 10,000 links and it can visit all of them and not be tired. But whenever you're building for a human, like even the 10th link is very far away on Google relative to the first link. And this is when re-ranking really, really matters.
Yeah. Yep.
Cool. I mean, the question I ask everyone at the end is, is there a question you feel like we have not asked? And is there a question you think we should be thinking more about when it comes to this kind of stuff?
Yeah, that's a good question, actually. I think at this point, all of this makes a lot of sense that, okay, we know the text modality quite well at this point. Like, even if we don't, then at least a lot more work has been done on this than, say, multimodal, which is the default way that humans interact with technology. Right? So I think the next thing that or the next sort of domain that retrieval or search people should focus on is multimodality, because I have done very limited work on that recently, and I found that, like for example, like when I talk to you about multimodal retrieval or embeddings, you think of clip, right? That's the way to go about it. There's so much been done on clip, like there's siglip and there's so many other encoders on top of that. So there's probably 20 architectures based on top of clip, and you could use any of them to build your baseline. But the thing is, if you run some benchmarks, you'll realize that the original clip and the one that is being used by default in other places we've come a long way from there, but not a lot of work and content has been written on top of it. I think multimodality is going to be the next sort of wave. And so we should think of building more benchmarks that deal with multimodal data retrieval and better baselines and better guides for choosing the right multimodal models. So this is the good question would be like, what is the baseline multimodal RAG? The answer to which I don't know. So yeah, that's the question I probably should. Yeah.
I find that Cohere's models now can do a lot more RAG over like tons of PDFs, but it's actually unclear whether they can be used for like scenes in movies or audio clips or like podcasts.
Yeah.
This is just the P at the table. So this is definitely something worth thinking about. And I'm excited to see some more work from the LanceDB team about multimodal work. Is there anything else you wanted to say before we end the session?
This was fun. I mean, if I do some more research on top of this, happy to come back and give another talk.
Of course. Thank you so much. Take care, everybody. We'll send a follow-up afterwards.
Bye.